This proposition deals with some properties of Legendre symbol. The first property is that Legendre symbol depends only on the residue of A modulo P. Second property states that Legendre symbol AB by P is equal to the Legendre symbol A by P into Legendre symbol B by P. Third property states that for B prime to P, the Legendre symbol AB square by P will be equal to Legendre symbol A by P. Fourth property states that Legendre symbol 1 by P is equal to 1 and minus 1 by P is equal to minus 1 raised to P minus 1 by 2. Let us prove each of these properties. The first property, that is, the Legendre symbol depends only on the residue of A modulo P, is obvious from the definition itself. The second property gives us the value of Legendre symbol AB by P. We know that this is equal to AB whole raised to P minus 1 by 2 using previous proposition, and that is equal to A raised to P minus 1 by 2 into B raised to P minus 1 by 2. Again, by applying the previous proposition, we can write A raised to P minus 1 by 2 as Legendre symbol A by P. Similarly, B raised to P minus 1 by 2 is equal to Legendre symbol B by P. Now, moving on to third property, we need to consider AB square by P. This can be expressed as A by P into B by P whole square using the second property, and this is equal to Legendre symbol A by P into 1 square. Since B by P, the Legendre symbol will be either plus or minus 1, as the GCD of B and P is equal to 1. So P won't be dividing our B. Hence, the Legendre symbol can have either plus 1 or minus 1 as its value. In either case, Legendre symbol B by P won't be equal to 0. In all these cases, we will have the result equal to Legendre symbol A by P. Now, for the fourth property, we can observe that Legendre symbol 1 by P is equal to 1, since 1 can be expressed as 1 square, which means that 1 is a square or a quadratic residue modulo P. So, Legendre symbol will be equal to 1. Also, we can write minus 1 by P as minus 1 raised to P minus 1 by 2 using previous proposition. Now, to evaluate Legendre symbol of the form A by P, we can first factorize A. For example, if A is equal to 2 raised to R into B, where B is odd, then Legendre symbol A by P is equal to 2 by P raised to R into Legendre symbol B by. To evaluate the right side, first we will show how to evaluate Legendre symbol 2 by P. Legendre symbol 2 by P is evaluated in this proposition as minus 1 raised to P square minus 1 by 8, which will be equal to 1 if P is congruent to plus or minus 1 modulo 8 and equal to minus 1 if P is congruent to plus or minus 3 modulo 8. For the proof, let us consider the function on the right side of the equation in the statement of our proposition. Let us label it as function f. Let f of n be defined as minus 1 raised to n square minus 1 by 8 for odd values of n and equal to 0 for even values of n. Then we will need to show that this f of p is equal to Legendre symbol 2 by p. Now, since p square minus 1 is equal to p plus 1 into p minus 1 for every odd prime p, we can see that one of these factors, p plus 1 and p minus 1, will be a multiple of 4 and other will be a multiple of 2. So, the product p plus 1 into p minus 1 will be a multiple of 8. Hence, we can write p square minus 1 congruent to 0 modulo 8, or we can express it as p square congruent to 1 modulo 8. P square congruent to 1 modulo 8 implies that 8 divides p square minus 1, but we know that n divides q minus 1 implies that there exists a primitive nth root of unity in fq. Here we have fp square. Instead of q, we have p square here. So, fp square contains a primitive 8th root of unity. Now, let zeta, element of fp square, denote a primitive 8th root of unity. Then, primitive 8th root means that zeta raised to 8 will be equal to 1, but zeta raised to j won't be equal to 1 for 1 less than or equal to j less than 8. Therefore, zeta raised to 4 must be equal to the square root of zeta raised to 8, which can have either plus or minus 1 as value, but we have already stated that zeta raised to j won't be equal to 1 for j less than 8. So, the only possibility is that this must be equal to minus 1. Now, we define a Gaussian sum G equal to sigma j varying from 0 to 7 f of j into zeta raised to j. This is in fact a Gauss sum, which is a finite sum involving roots of unity. Then G is equal to f of 0 into zeta raised to 0 is 0. Next is plus f of 1, which is 1 into zeta raised to 1, plus f of 2 is 0 into zeta square is 0. Next is plus f of 3 is minus 1 into zeta raised to 3, plus f of 4 is 0 into zeta raised to 4, plus f of 5 is minus 1 into zeta raised to 5, f of 6 is 0, plus f of 7 into zeta raised to 7 will be plus zeta raised to 7, so that G is equal to zeta minus zeta cube minus zeta raised to 5 plus zeta raised to 7. That can be written as zeta minus zeta cube minus zeta raised to 5 can be expressed as zeta raised to 4 into zeta, which is equal to minus zeta, since zeta raised to 4 is minus 1. So minus theta raised to 5 will be equal to plus theta. And similarly, theta raised to 7 can be expressed as theta raised to 4 into theta raised to 3, which is equal to minus theta cube. So we can substitute minus theta cube for theta raised to 7. So G becomes twice theta minus theta cube. Similarly, we can express G square as the square of this expression, which is 4 into theta minus theta cube whole square, and that can be expanded as theta square plus theta raised to 6 minus 2 into theta raised to 4, and that will be equal to 4 into theta square plus theta raised to 6 can be expressed as theta raised to 4 into theta square, which will be minus theta square. So theta raised to 6 can be replaced with minus theta square minus 2 into theta raised to 4 is minus 1. So minus 1 into minus 2 will be plus 2. This will be equal to 4 into 0 plus 2, which is 8. So we have G square is equal to 8. Thus, in FP square, we have G raised to P is equal to G square raised to P minus 1 by 2 into G, which is obvious, and we can replace G square with 8 to obtain 8 raised to P minus 1 by 2 into G. And we know that A raised to P minus 1 by 2 is equal to Legendre symbol A by P. So here 8 raised to P minus 1 by 2 can be expressed as Legendre symbol 8 by P into G is here. And we know that 8 is 2 cube. So it can be expressed as 2 by P cube into G, which can be expressed as 2 by P into G. Since 2 by P square will be equal to the square of either plus or minus 1, which will be equal to plus 1. So we can replace 2 by P whole cube with Legendre symbol 2 by P. Let us label this as equation 1, which gives the value of G raised to P as Legendre symbol 2 by P into G. Now let us try to evaluate G raised to P using some other techniques. On the other hand, G raised to P, which is equal to summation over J varying from 0 to 7 f of J into theta raised to J whole raised to P, which can be expressed as summation over J varying from 0 to 7 f of J raised to P into theta raised to J whole raised to P. Using the result, A plus B whole raised to P is equal to A raised to P plus B raised to P in FP square. Also, notice that f of J raised to P is equal to f of J. Since if f of J is equal to 0, then f of J raised to P will be equal to 0. If f of J is equal to minus 1, then f of J whole raised to P will be equal to minus 1 since P is odd. Similarly, if f of J is equal to plus 1, f of J whole raised to P will be equal to plus 1 also. So in general, we can write f of J raised to P is equal to f of J. Applying this result, we get g raised to p is equal to summation over j varying from 0 to 7 f of j. We write f of j instead of this f of j whole raised to p into theta raised to jp. Note that f of j is equal to f of p into f of pj. Since f of pj is equal to minus 1 raised to p square j square minus 1 divided by 8 using the definition of f, and that can be expressed as minus 1 raised to p square j square minus j square plus j square. I am adding and subtracting j square here so that the value doesn't get changed. Minus 1 is already there. All thing divided by 8 is equal to minus 1 raised to, grouping these first two terms together, we can write minus 1 raised to j square into p square minus 1 plus j square minus 1 divided by 8. And this can be expressed as minus 1 raised to j square into p square minus 1 by 8 into minus 1 raised to j square minus 1 by 8. The first quantity on the right side is minus 1 raised to p square minus 1 by 8 all raised to j square, which can be expressed as f of p all raised to j square. So this first quantity can be replaced with f of p all raised to j square. Similarly, this second quantity is f of j. Therefore, f of p into f of pj will be equal to f of p into this expression, which will give f of p all raised to j square plus 1 into f of j. If j is odd, j square plus 1 will be even. Therefore, f of p all raised to j square plus 1 will be plus or minus 1 raised to an even number, which will be equal to plus 1. And in that case, f of p into f of pj will be equal to f of j itself, since this quantity will become plus 1. Now, if j is even, then f of j is 0 and f of pj is also 0. So, if j is even as well, this relation will be satisfied, since both LHS, in particular f of pj and the RHS, that is f of j, will be 0. So this will be satisfied when j is either odd or even. We have already obtained that g raised to p is equal to summation over j varying from 0 to 7 f of j into theta raised to pj. Now we can replace f of j by f of p into f of pj, so that we can write summation over j varying from 0 to 7 f of p into f of pj into theta raised to pj, which is equal to f of p. Since this function is independent of the variable j, we can take f of p outside the summation. Summation j varying from 0 to 7 f of pj into theta raised to pj. Now we can make a change of variables. Here the variable of summation was j, where j varies from 0 to 7. Now we do the substitution. j dash equal to pj modulo 8. Then we have j dash running through 0 to 7 when j does so. This is possible since the collection pj where j varies from 0 to 7 is a complete set of residues which we can verify easily since there are exactly 8 elements in this set and none of them are congruent to another element. If pj1 is congruent to pj2 for some elements from this set, then it would imply that j1 congruent to j2 modulo 8. Since the GCD of p and 8 is equal to 1. But this cannot happen since j1 and j2 are two distinct elements from the set 0, 1, 2, etc. 7. And we know that this is a complete set of residues. So these elements are not congruent to one another. So this cannot happen. Hence, for two distinct elements pj1 and pj2 from this set, we can conclude that they will be incongruent. So pj1 not congruent to pj2 if j1 not equal to j2. Thus, we have seen that this is a complete set of residues. Hence, whenever j varies from 0 to 7, the value of pj also have the same variation when considered modulo 8. Now, we can replace the variable j by j dash to obtain the expression f of p into j dash varying from 0 to 7 f of j dash by replacing pj with j dash into zeta raised to j dash. And this can be expressed as f of p into, we can compare the expression given here to the definition of g and can observe that this is in fact g. Let us label this equation as equation 2. Now comparing the two relations 1 and 2, we have the right side of first expression was Legendre symbol 2 by p into g and the RHS of the second relation is f of p into g. This implies that f of p is equal to Legendre symbol 2 by p as required for the proof of our proposition. This is possible since g is not equal to 0, we were able to cancel g from both sides of this equation. This is clear since we were able to compute the value of g square as 8. So it is obvious that g cannot be 0. So we were able to cancel g from these expressions. Thus, the proof of our proposition is complete.